activity, and I found very, very nice, very, very inspiring, and thanks to some of you who have been here for quite some time already. Of course, we would all like to welcome the others who are here for this workshop. We were expecting some people from the Newton Institute, actually. Susan Gowans. For some reason, she's not here. I don't have my mobile phone on me, so maybe she's desperately trying to call me. But we don't know what happens. She might just be stuck in traffic or whatever. So, sorry?
Or trains.
Or trains, or yeah, I don't know. I mean, so I think what I would like to do, even though they are not here, or we all want to thank the Newton Institute because they have basically 100% sponsored this event very, very generously. So this was the first satellite program. And for those who don't know, I mean, I had some discussions yesterday with people, and the knowledge about the Newton Institute is varying. So the Newton Institute is an institute to promote mathematics in the United Kingdom, and they are based in Cambridge, and their usual modus of operation is that you apply there you can apply to the Newton Institute to hold workshops of various sizes and programs, like longer residential programs, and I think a few other things, like they have some scholarships, and also you can do research in pairs, I believe. Things like that they normally do, everything more or less resident in Cambridge. Now, they have been granted an additional amount of money not too long ago, and then they were desperate to spend it, and they consulted the community. And as part of this consultation, it was decided that they should also set up satellite programs, like residential programs, but not in Cambridge, but rather at other universities. So you could apply for this, and we did apply to BSNI, basically started this off, and then other organizers came in. I will name them in a minute, and then we put in the proposal, and it got funded, and we were the first, or we are the first of these satellite programs, the pilot satellite program, so to speak, the first satellite, the Sputnik, whatever you want to call this, and they pretty much treated us like a guinea pig, but then, of course, as a guinea pig, you get all sorts of goodies all the time and so on, so they were very generous with us, and helped us launching this, and they want to, of course, draw on our experience, and they have also further satellite programs already lined up. And the success of this, I think, will help to establish these satellite programs as a more or less permanent thing, at least as long as the money lasts. All right, so therefore we want to thank the Newton Institute once again. I would also like to mention the organizers of the program and this workshop, and this is Giulia Parigi, she's here now, and also Lea Oljacha. She is not here because she just started a new job, a recent development, so she had to basically leave this program halfway through, unfortunately. And then we have Jeroen Wouters, who's also here, and Tobias Kuna. And Valerio is not here, but might or might not show up, I don't know. Anyway, he helped us also with various things and is part of the organizing team. And then we want to thank Pauline Wayman. I guess many of you had electronic kind of email conversations with Pauline. She is on a well-deserved holiday now. Sorry?
Very well-deserved.
A well-deserved holiday. I do have a card in my office, and originally we bought something for Pauline, and we will give it to her later on. Originally, I had this idea that we just the organizers sign, but then I thought, why not everyone? So we were passing, because you all had, contact with Pauline in one way or another. So I thought I pass this around later on, and then who hasn't yet signed it could sign it as a. Sorry. Oh yeah. Speaking about the scientific committee, we have a scientific committee as well. I would like to thank those people as well. So this is Antje Weissamer, who's just entered the door, and Mike Cullen, who's also here. And then who else was part of the scientific committee? Georg Gottwald, who could not make it here from Australia. Paul Williams, who was here quite a lot, is not here right now, but also provided lots of input. And then we have Mario Müssermeier. And I hope I have Michael Gill. Michael Gill, of course, yes, Michael Gill was also here and also part of the scientific committee. And they gave us lots of very, very useful advice, like also in terms of estimating the numbers. I mean, there's something I vividly remember. Michael Collin was making that point. You know, he was saying, you know, please reckon with on the order of 15 like external people being here at any one time, and that number proved to be an extremely accurate forecast, I have to say. So it was yeah, we were reckoning with more like 10, but that would have been not enough. Anyway, so thank you very much to the scientific committee, and I think this I will leave it with that and hand over to our chairman, Giulia Carigi, and
thanks to Jochen, of course. And okay, hello everyone. So we start our day with Romain Pic. Have half an hour, including questions. Floor is yours.
Okay. Okay. And this is the microphone, so if you could stay on. Okay. There. Okay. So, hi everyone. It's going to be hard to look both ways, but I'll try to make it. So I'm going to present a work entitled Mathematical Properties of Continuous Ranked Probability Score Forecasting. And it's a work I've done with my supervisors, Clément Dombré, Philippe Navot, and Maxime Tayarda. And so I'll try to walk you through it and keep it quite easy since it's mostly theoretical results. So I'll start by introducing probabilistic forecasting. It will be a quick introduction, and then I'll present distributional regression and statistical learning, how we can combine them with probabilistic forecasting and obtain some results that we'll see after. So when you want to look at the weather forecast, for example, from the Met Office here, you have this kind of summary of your day. And so you have different types of information. Some information are some kind of pictograms that are the little suns or the clouds that will say that it's likely to be cloudy or sunny at that given time. And there is also another type of information that we have here for the chance of precipitation, which is, it's not only if it's going to rain or not, it's the probability and so the uncertainty associated to that forecast. And that's that might seem like a simple view of forecasting, but it's quite interesting to see that it has already some of the main components that we want to have in probabilistic forecasting. And so when at the beginning of the past century, Ernest Cook said something that is that any forecaster, when they make some forecast, they know that sometimes they feel more confident than others, and they have to share that information, and that this information is important, and that it's part of the prediction. Because it's not the same thing to say that it's going to rain today than saying that I'm 50% sure that it's going to rain today. And so with that in mind, people have developed various approaches to predict quantities over the future. And so a very basic approach is point forecasting. So for example, you want to predict the mean or a quantile associated to your, for example, the precipitation. And so that's the very basic step that does not contain information about the uncertainty of your prediction. And when we want to go further, we can use some ensemble forecasting. So we have different members that will somehow take into account the uncertainty that we make into our forecast, given different scenarii, for example. And a last approach that I will focus on today is distribution forecasting, where you predict or you give something associated to the distribution of the process that you want to study. So, for example, a cumulative distribution function or a density function or something like that. And so when we have these approaches, we need to evaluate them to say which one is better and which one we want to keep in the end and show to the public, for example. And so in point forecasting, it's kind of well known that we can use, for example, the squared error for when we predict the mean, or the pinball loss when we predict the quantile. But what seems to be harder is in what happens in probabilistic forecasting, because we use two different types of objects. We use a distribution on one side that we predict, and on the other side, when we observe, for example, the quantity of rain today during 1 hour, then it's just one observation, and it's not the same kind of object. And so the question is, how can we compare these two? And what we use are scoring rules, and so they are this kind of analog to loss functions objects that will enable us to compare these. And the scoring rule that we will focus on today is the continuous ranked probability score, that I will call from now on the CRPS. And so what this CRPS does is that so this cost associated to this forecast for this given observation Y, we are going to compare the CDF of our forecast. So here in blue, that we have in blue on the slide, and the empirical CDF associated to our observation. So we assume that we only saw this one event, so it has a 100% chance of occurrence, and so that's what we plot. And this CRPS is going to take the integrated squared loss between these two, so the space that you have between the two curves, integrated over the whole axis of values that this Y can take. And when we consider this from a more theoretical point of view, we want to study the expected CRPS. So if we say that the phenomenon that we want to study has a true distribution or a true CDF G, then we want to know if we make a different forecast F, how will be the average cost that we can expect in terms of CRPS. And when we take this notation, we have interesting tools that are, so if we compare the CRPS, which is the expected score when we predict F, but the true CDF is G, compared to if we were to predict the true distribution, then we have this integral with a positive quantity, and that shows that whenever we make prediction F that is different from the forecast, then we will have an expected CRPS that will be higher than the one that would have been if we make the forecast the true one, the G. And that property is the fact that the CRPS is strictly proper, because we only have the equality when F is equal to G. And so the only minimizer of that quantity is the true forecast that we want to look at. And so now that I've set up this framework, then we want to consider distributional regression in it and add some statistical learning and get some results of convergence. So when we consider distributional regression here, what I mean is that we take a variable of interest, like I said, the precipitation, that will be the Y in this case, and we have covariables that we can use to predict this Y. And for example, these covariables can be the temperature, the humidity, the pressure, and so on. And the forecaster's goal is to estimate the conditional distribution of Y given X, that we will note F star of X. And so we can use any model, but we want a model that if we give it some covariables as an input, it will have an output that will be our predicted CDF, this F hat of X. And one type of model that we can study are the statistical learning models that I'll present next. And in particular, once we have this model, we want to evaluate its performance and check if it's doing what we want, and if it's and maybe to compare it to other models that we might have. And in order to do that, we want to use this CRPS that I introduced before. And as I was saying, one possible answer is to do some statistical learning. So we consider a training sample with n observation of the past phenomenon, and we want to learn from that in order to improve, to train our model and to have some prediction that will be based on this. And so we have the same kind of place of our model, but we have this n observation that will give some information to train our model. And so that's why we have this n that appears, as it will depend on the observation that we use. And so we have this, we consider these two quantities that are the risk for our predictor f hat of n. So we take the CRPS, as I said it before, but we just average over the observation that we might have, just to have something more comparable. And also we average over the observation that we will use to test, or to test our model. And what we want to compare this quantity to is the best theoretical risk that we can have, which is this RP of f star. That is, if we were to make if our prediction was the true CDF of y given x. And since we have the property, the strictly proper property, we know that the quantity that we will predict will always be larger than the theoretical one. And what we want to do is to minimize this first quantity and to have it reach the second one. And in that case, we can have two kind of theoretical questions that we might want to answer. And the first one would be, do we have consistency? Which means that can we prove that that we can construct an algorithm that for any given underlying distribution will converge to this RP of f star. And a second question that we will answer here is, can we know what is the best convergence rate that we can reach, that any algorithm can reach? And that's the question that I will answer today. So in order to do that, first we keep in mind the fact that in point regression, we need to restrain the class of distributions that we look at in order to have interesting results or valuable results on the convergence rate. And so we keep that in mind. And at the same time, we have to choose a definition of convergence that will be interesting for our case. And the one that we chose here is we try to minimize the maximal error on a given class of distribution. So that's the minimax error. And this minimax error in terms of distributional regression has this definition. And so the quantity that we want to study is this optimal minimax rate of convergence, that is a sequence AN that corresponds to a given class D, and it has to check two properties, and so the two conditions. And the first one is a lower bound. So it is that any algorithm f hat of n has to have a convergence rate that is larger than this AN with a prefactor epsilon for n large enough. And then we have an upper bound that if there exists an algorithm that has that goes faster or to a similar rate than this same one, then the rate that we found is in fact the optimal one, and so we cannot do better than that in terms of the dependence in n. And so that's with that definition in mind, we want to find the class of distribution D that will make it easier for us to have these two properties. And so the class of distribution that we are considering has three conditions. So the first one is a condition on the covariables, which is that X has to be bounded. Here I took from values between 0 and 1 for each dimension, but it can be generalized. And for example, it's not that foolish to assume that, because for example, if we take the humidity, then it's bounded between 0 and 100%, and so it might seem like still a useful case to consider. The second condition is a condition on the link to the fact that we're using a regression. So this is this hard formula, and what this says is that this quantity is linked to the dispersion of y given x, and this quantity has to remain bounded. Because if we were to have an underlying distribution of y given x that has a large dispersion, then it will be harder for us to reach convergence. And so we have to take into account this maximal, like this worse dispersion, kind of, to be able to have more information on our convergence. And the last condition is linked to the fact that we are using the CRPS, which is this regularity condition. And basically, what we are doing in our algorithm is that we want to learn from previous observation. And so we need some kind of regularity in order to say that if we are really close to a point that we already observed, then it might be what we want to say is that the true CDF will be regular, that it will vary slowly, locally, kind of, or at least it's controlled, and we have these two constants that will control this regularity. And now that we have that, we can try to first show that we have the lower bound. So for the lower bound, it's the kind of the simpler case where we use a trick where we get back to a case that is a point regression case, and in that case we already have results about this lower bound, so this lower minimax rate of convergence, and it is in n power minus 2h over 2h plus d. And so we have that. And now what we want to have is this upper bound, and in order to have this upper bound, we have to find an algorithm that will reach this upper bound that has to have the same an as we found here. And so the algorithm that we chose is the k-nearest neighbor algorithm. And this algorithm, some of you might be familiar with it, but even if you're not, here we are in a distributional regression. And so what we do is that if we take a new observation of the covariables x, then we will compare it to the previous observation. Here we have x1 to x20, and we will only take the k nearest neighbor. So in this case, if we only take the 5 nearest neighbors, we will only use the empirical CDF at these 5 points to average them and to use it as our forecast. And this might seem like a simple method, but it's still interesting because it is linked to analogs method that were still used and performant at least a few years ago still. And now that we have that, we want to obtain this upper bound. And in order to do that, we basically use the properties that we have for our class D, and we obtain this upper bound that will depend on many constants that we have introduced before, and the value of k, so the number of neighbors, that has to depend on n. And so that's for a fixed, for a given n. And in order to find the best bound, we choose the value of k so that it's the tightest upper bound. And in the case where we chose it to be the tightest upper bound, we find the same value of an, so the same dependency of this upper bound is in n power minus 2h over 2h plus d. And so in that case, we found this optimal rate of convergence. Just to summarize what I've showed here. So we found this optimal rate of convergence for distributional regression. Maybe you've not seen it, but in this case, I only showed it for dimension d larger or equal to 2. You might wonder what happens in dimension 1. So for just for the k-nearest neighbors, the two bounds don't meet because we had something not strict enough, maybe. But anyway, we also showed it on our work on kernel methods, and in that case, we have no difference between dimension 1 and the others. And in that case, we still find the same convergence, optimal convergence rate. And so we have this result for any d. And just to make it clear that this result does not only concern methods that are minimizing the CRPS, but also on methods that just will use the CRPS as a verification. And if you check this quantity, so this expected CRPS, it has to have this optimal minimax rate, even if you're not minimizing it. And on the way, we also obtain upper bounds on the convergence rate for the k-nearest neighbors. And this result on the classical CRPS can be extended to usual weighted CRPS. And some perspective of this work would be to study other algorithms, maybe a fancier algorithm, and to study also other definition of convergence based on other distances, and maybe to also adapt other classical results other from this optimal minimax rate of convergence. And if you want to check out the rest of the work, we have a preprint, and if you have questions, I'll be happy to answer it.
Thank you very much, Romain. Questions, comments?
I've heard people say that this CRPS tends to favour methods with the most accurate deterministic forecast, or make the most smallest error of the ensemble mean if you don't have a deterministic forecast. But one of the issues is to forecasters complain about is when deterministic forecast suddenly changes from one day to the next because of new data arriving, and they would have expected the ensemble from the previous day to indicate the possibility of this change occurring. So that's that needs a measure of reliability, and I think that people say that CRPS doesn't really give enough weight to reliability. It's much more the accuracy of the deterministic forecast. And watching your talk, you're really helping design around getting the right answer if there is a deterministic answer, rather than that there isn't a deterministic answer. You haven't described the whole system. So, have you sort of thought about those issues?
I do not really think about these kind of issues, but it's like some other works have shown the limitations of CRPS.
And there's certainly a very strong message from the users of the forecast that they can't really exploit an ensemble that sort of follows deterministic all the time, suddenly changing. They expect to have seen the alternative solution clearly signaled by the ensemble the day before.
Yeah, because so even if we look at it from a theoretical point of view, what this strictly proper property says is that the minimum is the right forecast, but it doesn't say that something near the minimum will be close enough to what will really happen. And so in that case, the CRPS or many other scores don't provide information about the fact that if you're close enough, then your prediction will be close enough in that term.
It's quite important in saying if it's used as a performance measure, then people will try and design the system to be as good as they can in that measure. Yeah. And that means they'll really design the system to be good at deterministic forecasting rather than ensemble forecasting, which is actually not what it wants. So there is an issue there to talk about. I'm sort of raising it after your talk, it's probably a rise in future talks as well. So get that issue on the table and any other talks to address that.
So what are two questions? First of all, is the D is the number of covariates?
Yeah, it's the dimension of the covariates.
Okay. And then the other question, so this is a, I was just thinking about your conditions. So you have very little. So I think the conditions are actually quite kind of general, right?
Yeah.
I mean, they look a bit daunting, but if you think of it, these are. I don't feel these are very hard conditions because you seem to have very few conditions on the target, like on Y.
Yeah.
Right. So one thing I was thinking is, if you look at the CRPS condition, which is kind of hold that condition in the covariates,
yeah.
Does that imply a lower bound on the dispersion? I'm just trying to get my head around these conditions. No, because so I would expect, you know, if the dispersion is very small, and then you shift the covariates a bit, and you have two peaks basically, and then they move apart. Does this not mean that the L2 gets suddenly very big?
Yeah. If you have that case, then you will have distributions that are close in terms of covariates, but that will be quite different in terms of CRPS or in terms of L2 norm, because they will not overlap or stuff like that. And so in that case, you'll still have this order condition, but you will have like really large values of C or stuff like that to bound it, and then basically the constants in front of your convergence will be unusable.
But okay, so then for your class, the constant C has to be uniform.
Yeah, okay. It's the same for any.
Right. Okay.
I may add words open. So in the paper, we also have the weight of convergence, not only in terms of M, but also in terms of M and C. And it's indeed like you mentioned, if M is larger, then the weight gets worse, and so on.
Okay.
For simplicity, he has shown only the dependency in M.
Right. I'm just trying to kind of get my head around what this actually says. Thank you very much.
Yes.
So it's just this specific question. What is this F star of X?
This F star of X is basically it's the CDF of the true CDF of Y given X. So that's the underlying distribution that we want to predict. And so we have these conditions on this underlying distribution. And so if this distribution is not friendly enough in terms of these two last conditions, then we'll have a convergence rate that will change.
Actually, I have another question. Sorry.
Just a second. Let's see if there are questions.
You have no condition on the distribution of X itself, apart from number one, right, which is kind of the domain.
Yeah.
Is this correct?
Yeah,
all the conditions are on the conditional distribution, right?
Yeah, we do not have conditions.
Okay.
But the only condition that you might see is the fact that we have it bounded. So maybe if you want to study extreme distributions for X or for one of its covariates, then you might have issues.
I have a question actually. In the summary at the end, you mentioned other distances that you want to explore. Do you have any idea yet?
Yeah, so
anything that is more popular?
There are other distances that are more popular within this the community that want to like look at distribution and compare their distances and such. But since we come from the probabilistic forecasting, then the CRPS has this distance that is associated to it, and the other distances might not be connected to any score, but we still have in mind, for example, the Wasserstein distances and stuff like that. Or here we look at L2, but we might want to look at LP in general or something like that. But then we won't be able to go back to like the use of the CRPS underlying.
You have to readapt it.
Yeah, then you won't have any scoring rule and just have an expected.
Yeah. There are any other questions? Let's thank Romain again. think coffee is just about to be refreshed, and there's going to be more refreshments, and we start back at 11.